Привет всем! Я очень рад, что вы пришли на мой доклад, и очень рад, что я опять могу быть в прекрасном городе Киеве. Меня зовут Maciej, я приехал сегодня из Варшавы. Я работаю в небольшой софтвер-компании, ее называется Devoxx. Well, and that's kind of end of the talk in Russian and Ukrainian, and the rest will be in English. So thank you very much for coming. And as I've said, I'm working in quite a small software company called Devoxx. I do a lot of stuff there, but mostly working currently with Scala, stream processing engines, and this is my favorite child. It's called project called NoSQL, which is kind of graphical user interface for Flink. But today I'll be talking about something different. Today I'll start with kind of a reminiscence of a project that started like in 2012 when I was not so young, but certainly not experienced developer. And we had a project when we had to come up with quite strict performance scalability requirements. So we decided to use everything we could. We used event sourcing, CQRS, sagas, events loops, some weird NoSQL, not really reliable databases. And the most surprising thing is that the project ended up with kind of modest success, because we eventually migrated to Postgres, of course, but still, it was really challenging and stressful project for me. So when I started next project with not such strict performance requirements, we decided to go with kind of standard stack, that is MySQL, Spring Framework, there were no Spring Boot at that time, and so on. And for quite a few days or even weeks, I felt almost like on holiday. Why? Because I could put this magical annotation on my services, methods, or whatever, and they just worked, right? I didn't have to worry which saga should I use, what will happen with my event loop, when this projection will work, what will happen if something is made inconsistent. This just worked, and I felt like on holiday. Of course, until some more complex requirements came up, and that was kind of standard case of reservation. In our case, it was a reservation of SIM cards or something like that. So what do you do when you have this kind of code and you have to go deeper inside this transactional notation? What do you have inside transactional, inside any annotation? Well, of course, you have parameters. And inside transactional annotation, we have isolation parameter. And what value should we put there? And of course, the correct answer is this, default. And what is this default? Well, if you look into great Spring docs, you can see that Spring says, I don't know, just go and ask your database. They also have some default isolation level. And, well, it makes perfect sense. And of course, it makes your Spring code perfectly portable across database engines. So, what do? We go to our favorite database, be it Oracle, well, maybe not your favorite, MySQL, Postgres, or whatever, and you see, okay, so what are all these isolation levels about? And it turns out it's kind of fairly standard stuff. It's designed by ACID like almost 30 years ago. We start with some kind of basic sanity level, like read uncommitted, which protects us just from the, well, kind of really crazy things. Then we have kind of like first reasonable level read committed when we're safe from dirty reads from other transactions that may in the future abort. And this is kind of first reasonable default isolation levels. And quite a few databases like MySQL, Oracle, for them this is the default. But unfortunately, from time to time, we have requirements or situations or use cases where this is not enough, right? For example, when we have one guy who's want to make reservation of some object like SIM cards from the pool. Okay, he gets some number like 5, and his padruga is also doing some select. She gets the same number, but he's on a train with some really bad Wi-Fi connections. At least we have that in Poland. So she's faster than him. She commits the transaction, but then he uses the number that he got earlier, also commits, and we have a problem because some some of our conditions, requirements, consistency is violated. So what we can do here, of course we can use another Spring annotations, that is version, use optimistic locking and so on and so on. But let's see what can database give us. And the thing is that we can move to more safe isolation levels. ANSI standard defines repeatable read and serializable, and of course they give us better guarantees, but also they come with some kind of more or less heavy performance penalty. And some databases use this as their default, for example, Postgres. And at the top, we have kind of a holy grail of isolation that is serializable. And here things start to be a little bit, well, more complicated. Because it turns out that serializability has kind of two definitions in ANSI standard. One is more or less like this. It says that we can pretend that the transactions are performed, well, essentially single-threaded. Of course, under the hood, probably they won't be performed in that way, because that would be too underperformant. But still, we can assume that, yeah, all the transactions are performed just like single-threaded. But ANSI standard also defines isolation levels in a second way. That is by the absence or presence of certain kind of strange phenomena that we want to avoid. And with this definition, we can say that ANSI serializable is just like repeatable read, isolation level, and we don't have so-called phantom reads. That is, we don't want, during our transactions, from time to time to get new rows that were inserted, for example, by other transactions. And for a few years after designing ANSI standard, people thought that these definitions were the same. It only took them some time to realize that there are some subtleties and design some yet another isolation level that's called snapshot isolation, which is more or less saying that, okay, each transaction can be thought of as operating as on his or her kind of own private copy of the database. And it turns out that some databases, for example, notably Oracle, use this definition as their notion of serializability. And this is from some point of view correct, but still, this is not the case that, for example, in Oracle, we can assume that this serializability requirement just gives us this notion of single-threadedness. Because we can come up with some more elaborate and difficult example. That is, let's assume that we have husband and wife, they have family account, and each of them can go below 0 on their account's balance, provided that the sum of their balances is above 0. It's kind of reasonable, right? So we have husband, he has 30 on his account, wife has 50, and husband also has this amount, and the wife sets her balance to -20, and for her, it's okay, right? Because still total balance is 10, and husband at the same time wants to have -10 on his balance, and from his point of view, here, they will also be still in the black, right? They won't go below 0. But it turns out that these two transactions will commit, will break our consistency requirement. And here's the problem, because this situation may happen with this snapshot isolation level, because we don't have so-called wider locks on results of the different queries, right? And the Oracle developer will come up with a solution, of course. If you develop in Oracle, you know that this magic keyword called for update, and then we'll put some artificial lock, and everything will work okay. But I'm saying all of this to you to make you realize that these ANSI isolation levels are far from being kind of widely and exactly understood, right? At the beginning, there are some kind of rather simple notions, but then we end up with quite subtle differences. right? So this is what we usually recall when we talk about ANSI isolation levels. It turns out this is something more like this, and we can end up with even more complex stuff. This is a screenshot from a project called Hermitage, where the author, Martin Klepman, set out to understand how each of the major databases like MySQL, Postgres, Oracle, and so on, how do they realize their so-called isolation levels, what is their actual isolation levels, and how do they behave in certain situations. So if you look at this, this is kind of complex, right? Here, everything is more or less simple, but then there are really, really subtle differences. So if you have a gut feeling that you have some kind of strange threading performance transactional requirements, do yourself a favor, go to that page and see how your database is performing, right? Because almost 30 years of ANSI SQL and still isolation levels, at least the higher ones, are not so standard. Fortunately, we don't have to worry that much about it, because in Spring, we have another annotation. We have this annotation, and up until recently, this, as usual, Spring annotation enable another annotation, and that is this one. So we don't have to worry. MongoDB disable transactional, and everything is brilliant because, as we know as Mongo users, when you use Mongo, you don't need transactions, right? This is what the creators of Mongo used to say, right? Document model negates need for race transactions. 80–90% of applications don't need multi-document transactions at all. Well, and life was quite easy then because nobody wants to be in this 10 or 20%. Of course, there are some cases when it's not so easy. This is a slide from a presentation of my friend, it was like 5 or 6 years ago. And yeah, it was correct. Granted, no one should be building a banking system on MongoDB. And then this is the next slide of my friend's presentation. And yeah, he did that. He challenge accepted. He did this banking application in Mongo. I think he has quite more gray hair than he used to, but still, as far as I know, this application is working. So everything was quite simple. But recently, well, a year or two ago, Mongo creators starting to act a bit differently. So fully ACID transactions are coming to Mongo this summer. I think it was last year. And with this piece of puzzle, multi-document, multi-transaction guarantees, it's game over, right? Wow. So once you implement a feature, you say, yeah, it's highly needed. Well, everything okay. But you start to wonder, at least I started to wonder, because some year ago, well, I've been to many presentations where people say, okay, ACID is dead, now you need base, now you have Kafka theorem, and so on. And now there are so many databases in the world, some of them widely known, some not so widely known, and each of them are adding some transactional capabilities to their systems. Probably some of them work, probably some of them not so. But how is it that, well, apparently the trend is changing, and now transactional serializability are trendy again, right? Because a few years ago, we were learned, okay, so there's this Kyiv theorem, you can't have consistency when you have kind of web-scale transactions. And many people said, okay, Kyiv theorem is kind of mathematical theorem. It has proof. You cannot break it. Reality. You cannot escape these trade-offs between consistency and availability. So what happened in these few years, right? Did laws of physics change, or did we find some problem in the proof, or did anybody just forget about this Kyiv theorem? And turns out it's kind of good to go to the basics, because if we assume that something is kind of mathematical theorem, then probably it has some definitions. And if the proof is to be okay, then we have to have strict definitions. And this is kind of definitions from random block in the net, how to define consistency, availability, and partition tolerance in Kyiv theorem. And they at first look quite reasonable, but if you look closer, they're kind of wrong. For example, it says availability, at least one node must be available. Partitions, failure of the system is very rare. This is by no means strict. It cannot go to mathematical proof. So let's go to the original definition of Eric Brewer, how he understands that, and what changed, right? So he says, okay, firstly, partitions in the network are inevitable. And to model this notion of partition tolerance, we say that the partition is a phenomenon where we can lose arbitrarily many messages from any node to another. We just don't accept that there are some hackers who can mess around with our system. And when it comes to availability, he says that for distributed system to be available, every request received by a non-failing node, so by any non-failing node, not just one of them, must result in response. So this is kind of really, really strict and hard to achieve condition. And consistency, again, is quite complex. Under this consistency guarantee, they must exist a total order of operations. And, well, essentially, we may think of it that all operations, more or less, would appear on single instance, right? In this serializability isolation level, we would think about it as single-threaded, and here we can think about it as single instance. And if you think about this definition, it turns out that this theorem is not so, I would say, not so difficult. It's kind of simple corollary from all these definitions, because if you have a replicated database, well, of course you have to replicate your data. And if you replicate your data, well, you can do it synchronously or asynchronously. And in the first case, you, well, lose availability, and in an asynchronous way, you lose consistency. And the proof is quite simple, quite, as for such proofs, quite easy. So what does Kyiv theorem essentially mean to us? Why do people talk about them? And turns out it's not about the proof itself, but about making us think about all the trade-offs. And after a few years, people realized that it's not about availability, consistency, or partition tolerance only, but also about how our system behaves in kind of normal conditions. It's also about performance, like throughput and latency. Because even if I have perfectly consistent or available system, and it's like performing like one transaction per second or one transaction per minute, but it's also no use of it. And you think about, so it's all about trade-offs, and if you look about popular NoSQL databases like MongoDB, you can see that, yeah, they have all these knobs that allow us to reach this level of consistency, of availability, to make all these trade-offs with some tweaks. Like, for example, in Mongo, they have read can be 0, 1, majority, and also there can be different read consistencies. And again, in Mongo, first the defaults were so that it was fast, and after they got some enterprise client, the defaults changed, and now it's more safe. But researchers love to do research, and some of them turned out with the idea that there are even more shades of gray, and some of them, like Bailey Pekete, it was a few years ago, came up with a notion of high availability transactions, high available transactions. And what they mean by that is that they started to realize that between these kind of eventual consistency, whether everything is kind of blurry, and sequential consistency, as in Kyiv theorem, there are also even more kind of subtle definitions of consistency, and some of them can be weak enough that they can be achieved in high available systems, right? So there are some notions like monotonic read and writes, writes follows reads, that can be achieved without losing availability. And even to make stuff even more complex, they designed notions of so-called causal consistency and regularized consistency, which basically say that you can have more or less consistent view of the world, provided that this consistent view of the world is only for certain client who talks to one node in the database, which in many cases is kind of more than what you want. And if you, again, look at some kind of popular NoSQL database like Mongo, you can see that, yeah, from, I think, version 3.4 or something like that, there is notion of session, and it says, okay, you can group your operations with one kind of session, which has to be single-threaded, and so on and so forth, and then you can have some really strong notion of consistency, and you then don't have to care too much about the stuff that's replicated and so on. And if you look deep down into Mongo docs, you can see that at first you can look at it and say, okay, this is kind of technical blah, 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 blah. But if you find all those definitions that were on the previous slides, then it makes kind of sense, because you can recognize familiar patterns and start to understand what does this really mean. And if, of course, you can look at this long, long sentence, you discover the notions that we're looking for, and that is all this transaction stuff. Because so far, for the last few minutes, we've been talking mostly about this notion of theorem, consistency, and so on. But what does that leave us with in terms of transactionality? And turns out that, again, the situation is quite complex, because all those notions of consistency, again, this consistency has nothing to do with consistency as in ACID, because this is something a bit different. These are about behavior, single operations in distributed databases. And here we have this notion of isolation, which are about transactions spanning multiple operations in, well, probably not necessarily distributed databases. And how do they map to each other? It turns out that they kind of don't map at all, right? We can have this one, but not this one, and vice versa. And only after, at the top, we can have a notion of strict serializability, which is kind of, again, a holy grail, probably not easily achievable. That is the transactions that we can assume in our heads that are not only single-threaded, but on one database node. And again, if you look carefully about different knobs and settings in Mongo, you can check that using all those settings, you can reach different places on this graph with your one Mongo instance and make as many trade-offs as you want. But as we move towards the top of the picture, that we want greater and greater kind of guarantees of serializability and isolation, things are getting a bit more complex. And even if you look at, for example, Mongo kind of press releases, you can see that at first there's Mongo 4.0, and they support multi-document transactions on replica sets. Replica sets is basically Mongo setting when all of your data can fit to one machine, and you just replicate stuff for kind of availability. But still, you have just enough data to put it into one machine. And only in version 4.2, quite a few months later, they said, OK, now we can have transactions that can not only span multi-documents, but also they can span multiple shards, right? So this took them quite a lot, and there's some serious problems with achieving this distributed transaction spanning multiple shards. Because if you think about it, well, if you think about the settings when you have one primary replica of all your data in Mongo, and then you replicate stuff just to make availability, then this notion of multi-document transactions mostly is evaluated here on your primary replica. Of course, there are a lot of different difficult problems to solve with replication to the slaves, but still, the decision if transactions should be committed or aborted is on this primary replica. But if you have many shards, the situation is vastly different, because each of those shards is just independent of them. And they have to come up with some coordinated notion. Should this distributed transaction on many documents, should it commit or abort or whatever, right? And here comes the, well, unfamous notion of coordination protocols, mainly, oh, here it is, two-phase commit. For those of you who are, well, old enough, this reminds you kind of different world than we what are used to. And this is the world of JMS, MQ, of Oracle or Postgres, and XA transaction managers. Good old days or JEE and so on. So that was kind of a long time ago. And this is the world of two-phase commits, transaction managers, and so on. But since that, we've learned that two-phase commit is anti-availability protocol. And of course, this is true. Well, the only situations where this two-phase commit and XA transactions for me worked was when everything was in one data center, and what's more, the amount of traffic was no more than, like, I don't know, 5 transactions per minute, right? Then it more or less worked. But what about two-phase commit? Why it's called anti-availability protocol? And did people learn to come up with something with it? So two-phase commit is basically a protocol when you have coordinator systems, and they have to agree should transactions distributed between them should commit or abort. So coordinator says, okay, prepare for transactions to both of them. And they answer, yeah, I can commit. Yeah, I can commit. And then coordinator, what does he says? He thinks. Okay, everybody answered yes, we can commit. And he says, okay, commit. Okay, commit. And what do they do? Okay, I will commit. Okay, I will commit. And this is the end. So you can see, well, there are 2 problems exactly with this protocol. One is that you can see it's a bit chatty. But the other problem is that it's highly prone to blocking, because if coordinator, for example, your JE server dies at this moment, what can happen? Well, these systems don't know what to do. They wait for the answer from the coordinator, but the answer doesn't come, and they have to still keep their logs and transactions open. So what does then happen? Well, you call your grumpy system DBAs, and he says, oh, you stupid developers, I have to clean up for you. And you ask him politely to remove distributed logs, right? So this is why it's anti-availability protocol, because system DBAs are not highly available. But people came up with even more fancy algorithms. So once they realized that two-phase commit does not necessarily work, what did they come up with? Three-phase commit, which is kind of less blocking. It's not as blocking as two-phase commit, but you can see from the answer that it's even more chatty, and the latencies go even more high up. But this was kind of thing of the 80s, and in the beginning of the 90s, we got even more advanced distributed consensus protocols. And again, they are not so blocking as two-phase commit. They are quite performant. But the problem with them is what? Well, the problem with them, especially with Paxos, is I think not many people, apart from their creators, understand that. They are really highly, highly complex, and probably not for mere mortals like certainly like me. I don't know what about you. So where does this lead us? Is there any hope to achieve some sensible distributed transactions? I think we have to separate 2 notions with the distributed transactions thing. First, there are distributed transactions in heterogeneous systems, like, for example, microservices, when you have many, many systems that can be written in God knows who, by God knows who running, God knows where, and so on. And we cannot assume not much about how they cooperate and so on. And in this case, I think that the world came up with the idea that some kind of generic distributed coordination protocol is difficult to achieve. And if we have such a situation, we should leave ourselves with Segas. If we have some kind of message brokers, we can have this notion of at least once delivered and idempotence, or more fancy stuff like CRDTs. Probably some of you thought that all this talk was going to be about microservices and sagas. If so, then sorry. Because let's move to the second level of the diagram. That is not heterogeneous system, but homogeneous systems. And the primary example is, the notion of distributed database. When, in fact, we have one system, and the fact that it's distributed or replicated is kind of, I would say, implementation detail, right? And here, the participants of the system can know a lot more about each other, so they can come up with kind of more complex and, I would say, reliable protocols of communication. And I think this is the way how those so-called brave new SQL, or not really SQL database, appeared. And I want to just throw a quick glance on two of them. The first one is kind of more widely known. It's called Google Spanner, and it used to be kind of internal stuff for Google. Now it's available in their Google Cloud. And the author said something like this a few years ago, that, okay, we know that people assume that two-phase commit is expensive in terms of performance and availability, but we think that application developers are so stupid that it's better to not give those eventual consistent tools for them, but it's better to give them by default serializability and consistency, and figure out how to deal with performance problems later, right? So again, this is kind of bold claim, but they're at Google, so they can think about it. And the spanner looks from a really high point of view, more or less like this. Again, it's replicated, sharded database. It's not necessarily arbitrarily replicated, but yeah, it is replicated. And if you perform some single operations like writes or updates, those writes are replicated to the shards using this Paxos algorithm. So it's different than in Mongo, where we have primary replicas and secondary replicas. Here, each write is kind of more, it's more like involving some coordination algorithm. So again, at first they trade some availability. And when they want to have multi-operation transactions, they again employ some kind of transaction coordinator, more or less ad hoc. And then, again, they are also replicated. Those transaction coordinators, they form another, that's called Paxos group. And all this setup is a part of kind of wide two-phase commit operation. So this is how transaction goes. As you can see, this is quite complex architecture, and I think it's kind of a real engineering feat to bring it into kind of reliable work. But what's even more interesting, they put some additional Google secret sauce, because Google owns their own data centers, and they are able to put some additional stuff like atomic clocks, GPSs, and then they get a really interesting feature that is the notion of, they call it true time, and this is the notion of absolute time shared without kind of coordination between their data centers. And this whole architecture can give them guarantees of both consistency and serializability, as in multi-operation transaction isolation, right? So this is quite complex, elaborate architecture, and they trade off some of the availability, but they reason for that in this way. This quote goes from Eric Brewer, who's the inventor of theorem, and he says, okay, Google has their data centers that are so available that we can assume that, well, effectively partitions don't happen, we have consistent available system. And they further say, okay, and even if there's some major failure in our data centers and partitions do happen, then why do we need this availability? Probably if there's such major failure, then your website isn't working anyway. So you don't need available database when everything just broke, right? But this architecture is kind of quite complex, and people came up with the idea that maybe it's better to get rid of all these two-phase commits, backslash groups, totally, right? And one of the approaches, just a quick glance, is called Calvin. It's only started to be deployed kind of in commercial way by something called FaunaDB. And here, the idea is that we don't have such wild two-phase commits, but in the front of the clients, we have kind of distributed transaction log, and all of the clients just send their transaction declarations, not as in normal kind of DB transaction when we have begin, do something, and then after a while we do commit. No, they send, I want to do, in one transaction, I want to do this, and that read, and these two writes. And the inputs, the definitions of the transactions are replicated in this distributed transaction logs. And then in some kind of batches, they are sent to the nodes where real data, real operation happen. And the thing is that because these transactions are kind of declarative, the effects of the transactions are performed in kind of deterministic order or all nodes. So because the order of operations on each node is kind of deterministic, we don't have to worry about coordination. This is kind of a nice idea, at least for me as a Scala developer, because it reminds me of functional programming, right? We have declarative transactions, we split the definition of the transaction from execution, and of course we know no side effects, right? So in this situation, you kind of have begin transaction, do some updates or writes, then invoke some, I don't know, REST service or whatever, and then do all the writes. No, there are no additional side effects. So this is kind of, I think it's interesting idea, and I hope it's have some bright future. But currently, well, you may very well say that this is an area under research development, and what does it have to do with us, simple developers? And to end up with something kind of more familiar to all of us, we'll move to kind of a bit different transactional settings, and we'll move to message brokers, and especially to Kafka. Of course, now everybody knows what more or less Kafka is, but if somebody doesn't, I'll remind that Kafka isn't a message broker, but just a replicated data log where producers write to what we may think of a giant log file when each producer appends messages. They are some kind of magically replicated to other nodes, and then the consumers, they don't receive messages like in JMS or ActiveMQ or MQ, but they read from this long log file. How do they want? They can go further in the log, they can go back, and so on and so forth. So this is quite nice, simple architecture, which gives Kafka not only performance, but also nice features in terms of delivery and so on. So when we have message brokers, the idea of transactions usually can be associated with such situation. When you have some message broker, a good effective MQ or MQ, we want to read message, process it, send, for example, to some kind of Oracle database, and we want to do it just exactly once. So we want to be sure that we read the message from the queue and write it kind of atomically, right? And here, again, there's kind of notion of distributed transactions. So how does it fit in the picture of Kafka? Well, essentially, we can have three cases. First, we have some messages in Kafka. We can read from the topic, process them, and write somewhere else, for example, to database, HDFS, or whatever. Second question is, we want to ingest messages from external system, for example, database or whatever. We want process them, and spit to some Kafka topic. And the last one is we want to take messages from Kafka. This is the case of most streaming engines. We take messages from Kafka, process, and we throw it away to another Kafka topic. And what we want to solve is the idea to have exactly once deliver in such situation. And quite recently, a year or two ago, Kafka came up with the notion of came up with the notion of, well, transactions again. And the idea is, first we want to have the first property of ANSI transaction, that is atomicity. That is, we want to have transactional producer which writes messages to many Kafka topics or partitions, and we want them to be available to consumers, either all or none of them. So Kafka creators came up with, well, a notion of transactional coordinator, which is not so surprising. And this transaction coordinator under the hood, of course, has some additional Kafka topic. And the producers in this transactional setup, they send the notions of beginning or committing or aborting transaction to this coordinator. He can put some additional kind of metadata in the topics, and the messages are consumed by consumers only. This offset can move only if the producer commits the message, right? So this gives Kafka a notion of kind of read committed isolation, right? So first thing is we want to have atomic producer, either all messages are, well, produced to topics or none of them. The consumer can achieve read committed isolation level, and one additional caveat is, because Kafka is kind of message log where messages are read one by one in order, then we have, if we have long transactions, probably they can block a consumer a little bit. And this notion of atomic producer can give us quite nice property of exactly once delivery when we want to get some messages from Kafka topic, process them, and send to another Kafka topic of many of them. Because what happens is when consumer reads, I don't know, 10 messages, processes them, sends everything to the output topic. Then when we want to commit the transaction, we not only commit the messages to output topic, but we also commit the place in our source topic where we are to this kind of offset topic where Kafka remembers how many messages producer consumes. And this writing, both kind of normal messages and the notion of committing offsets, is part of the single atomic transaction. And this gives us the notion of exactly once delivery in Kafka, provided that everything, well, stays in the same Kafka cluster. So this is the idea when we read from Kafka topic and write to Kafka topic. But what about different situations? Well, it turns out we can do something, at least in some of them. If we want to ingest some data from database and put it to Kafka topics, for example, if we have some incremental import from some kind of database to Kafka, then we can store the last row or document where we stopped our import, also in kind of auxiliary Kafka topic, and we can commit it together with our kind of normal messages, again, atomically, and then we can have kind of nice exactly once semantics for our import. And if we want to write data from Kafka topic to database, and here we have a notion of transactions on multiple documents, collections, or tables, we can place in this Kafka topic where we stopped our export, again, transactionally in some auxiliary data table collection or whatever do we have in our database. But in generic case, I think it's kind of not really possible to have some kind of generic consensus of exactly once delivery where here we have some kind of arbitrary microservice or whatever. Then we probably want to resort to at least once delivery and idempotems, which is kind of nice features of Kafka anyway. So Kafka transactions are really interesting because they give us atomicity guarantees when it comes to data production. They give us kind of notion of effectively exactly once in many, many cases. But if you think a bit, those transactions give us quite weak isolation, just read committed. And the notion of more isolated transactions on many partitions, on many Kafka partitions are still kind of, I think, unsolved problem. There are some notions from the creators of Apache Flink. They are working on that, but it's kind of, I think it's still more or less work in progress. Okay, our time's almost up. So, what all of this can give us? What can we learn from that? Well, I think the first notion is that it's good to remember that even the things that we assume as granted as well-known SSD transactions are not always so obvious, and there are quite a few subtleties and caveats that we should be careful about. The second thing is that it's good to read the documentation of all these modern databases and dig about a bit deeper than this marketing bullshit that they have on, well, usually the first pages. Because underneath, probably the documentation can be translated to some kind of common definitions that I've shown you, and only then we can compare which properties can we achieve in which settings and which configuration of those databases. And the first thing is that, well, the laws of nature probably don't change, and there are some limitations that won't change. For example, the speed of light won't change, so we have some barriers of latency, although probably in Spring 11 there will be annotation adjust speed of light or something like that. But on the other hand, there are some constraints that we should evaluate every once in a while, because hardware advances, software also advances, and some trade-offs that we made, I don't know, a few years ago can be not valid anymore. They don't change as fast as JavaScript frameworks, so we shouldn't probably reassess them every month, but every year, maybe it's interesting. And if you want to learn more about such topics, I recommend this book and the other one, which is kind of new one, but this is very good, and some blogs and pages. All the authors offer really good knowledge about different distributed system techniques and databases. And yeah, I think that's all. Ja, Denis, to wam ponравилось. If you have any questions, then you can ask now, or I'll be somewhere around. Oh, there is good.
I often see databases being used in combination with Hibernate or with the OR mapping, and then you have this implicit caching. And to my understanding, this makes also transactions weaker, because sometimes you have the cache, sometimes you have the real database, and you are more away from the database. Thank you.
Yeah, I mean, what you are saying probably is kind of when you use cache local to your application, then effectively you make your database, well, more distributed, right? And you have to take care about consistency by yourself, which usually ends up, well, in nasty bugs, right? Yeah, this is very good remark. Well, if nothing then, thank you very much, and I hope you enjoyed the conference.